The other thing we're really interested in, of course, is what are the energies that are given by the solutions. So the energies follow this equation. The energies depend just on L, and they don't depend on M at all. And we get h bar squared over 2I times L, times L plus 1. And so these are the generic, these are the energies that are given. So for rotational energies, we often change the notation here. We reserve L to talk about orbitals. And so we let L equal J, and we also call h bar squared over 2I. We collect all these constants to one constant B that we call the rotational constant. And so we can rewrite this expression as B times J plus 1. And these are the energies of a rigid rotator. So it's a fairly simple expression. It's almost the square of L, of this L quantum number, but not quite, because we have this plus 1 in here. So it's almost B times J squared, but instead it's B times J plus 1. Now the L squared operator ends up also being useful because all the spherical harmonics are also eigenfunctions of the L squared operator. And so we can get exact values of the angular momentum, at least the square of the angular momentum, from these wave functions. And so the expressions that describe this for the spherical harmonics, so L squared operating on YLM, gives us h bar squared times L plus 1. Or if we want to write this in terms of J, h bar squared times J plus 1. So almost the same as the energy, just without the 2 over I that's present. And it turns out that the Z component of the angular momentum is also, the spherical harmonics are also eigenfunctions of this. And if we operate LZ on the spherical harmonics, we get that the Z component of the angular momentum is equal to M times h bar, right, where M is our other quantum number. And M is often called either M sub L or M sub J. Again, this can range from negative L negative L to positive L. So what do these energy levels look like? So if we go ahead and plug this in, if we kind of plot these out like we did for the harmonic oscillator. So if we take J equals 0, E equals 0, that one's pretty straightforward. And the molecule is not rotating. So unlike the harmonic oscillator, there is no 0-point energy for rotation. So once a molecule stops rotating, it's not rotating. But you can never stop it vibrating. For J equals 1, we get that the energy is equal to 2B. So this gap here is 2B. J equals 2, the energy is equal to 6B. And I'm getting these values from just plugging it into our expression, right? B times J plus 1. Right, so if we plug in 1, we'll get 1 times 2. If we plug in 2, we'll get 2 times 3, which is 6. And we could continue this up. Right, and so the gap becomes 4B here. And what we'll see is that the differences in energy are always equal to 2B times J plus 1. We can show that mathematically. You can look at my lecture notes. I go through that derivation specifically. Now we often switch this to wave numbers. So B in wave numbers, we give the symbol B tilde when we're doing rotational spectroscopy. And instead of B, right, so we define B as h bar squared over 2I. B tilde is switching the units, and we get, so we'll go ahead and write out the pi specifically, h over 8 pi squared c times I. That gives you the same thing, right, the same thing as we saw for B. This is just switching from units of not even joules. I believe this is in units of hertz. So joules, not hertz, and this is in units of wave numbers.